Okay, there we go. So sorry about that. Right, so we started talking about we are talking about non-parametric approaches or alternatives to the one sample, two sample, and we will see an example of the ANOVA procedures that we introduced in lecture sets 2, 3, and 4. So far, we have seen alternatives to the one sample t-test and the paired t-test. Those alternatives were the sign test and the signed rank test. In lecture set 10, which is the lecture set that we're going to work through today, we are going to see an alternative to the independent two-sample t-test. And we call this alternative the Wilcoxon Rank-Sum Test. It's also known as the Mann-Whitney test, the Wilcoxon Mann-Whitney test. It has a lot of different names. But the idea is it's very similar to what we saw in the case of the signed rank test. We are going to use the ranks of the observations in the data set, which means that we're going to induce an order on said observations, and we're going to use those ranks to test for a significance difference in population medians. All right, so the example that we're going to use is a comparison of average or median salaries between genders for professors from the same university. So the rationale here is that salary is a well-known example of a skewed variable. So salary distributions always tend to be right skewed because you have the majority of people working at the lower level incomes and only a few people working for higher level incomes, which creates natural skewness. All right, so if we want to make a statement to compare the median salaries of the male and the female populations, and we have sample sizes like those that were given on the previous slide, so sample size of 10 and a sample size of 13, for example, the central limit theorem is not going to provide us any protection, or the central limit theorem, I should say, is not going to allow us to assume approximate normality of the sample means in those particular cases. So just like in the previous examples, we require some sort of alternative test so that we can still make a comparison. So when we have independent samples, our alternative is the Wilcoxon Rank-Sum Test. All right. So the Rank-Sum Test works pretty much like the other hypothesis tests that we have studied in this course. We start off with a set of assumptions, and then we work through a 6-step procedure to compute or to determine if we have evidence for or against the null. So the assumptions of the Rank-Sum Test are that each sample is a simple random sample from the population of interest. The samples are independent of one another, and that the populations have the same shape. So we don't require them to be symmetric or normal, but we do require them to be of the same shape, right? So in this particular example with the salaries, we have the male and female populations, and those are both going to be right skewed populations. The 6 steps of our hypothesis testing procedure are very similar to what we saw before. On step 3, we're going to use the sum of the ranks for sample 1. So this, like the other two sample inferential procedures we've talked about, means that we will have to make a declaration of which population is our 1 population and which one is the 2 population. Because if it's a directional test, this will make a difference in setting up the alternative. On step 4, we're going to use a new table to compute the critical value and the p-values. And we're going to talk a little bit about this momentarily. And then step 5 and step 6 operate in the same way that they did beforehand. Okay. So we have already talked about the idea of a location shift when we studied the paired sampling techniques in lecture set number 9. So the idea here is pretty much the same. We have 2 different populations, and what we're trying to do is determine if the centers of those distributions are not aligned with one another. So we're basically asking if there's evidence that one population, the center of one of the distributions is different from the center of the other distributions. Okay, in terms of taking the ranks of the data, we would have a number of expectations of how the ranks or the sum of the ranks are going to behave under each of the different possible outcomes. So for example, if you have two samples, you rank the data in each sample, you would expect the sum of the ranks from each sample to be about the same if the populations have the same median. If the median of population 1 is less than that of population 2, then the sum of the ranks from population 1, or from sample 1 rather, should be smaller than the sum of the ranks from sample 2. And if the median of population 1 is greater than that of population 2, then the sum of the ranks from sample 1 should be greater than the sum of the ranks from sample 2. So in this sense, we have a pretty logical expectation of how we would expect the test statistic to behave in comparison to the sum of the ranks from the other sample. For the Wilcoxon Rank-Sum Test, we have the same null and alternative hypotheses, or the same options for the null and the alternative hypotheses that we had when we studied the signed rank test. So we can do the general test of no difference between the distributions or between the population medians. We can do an upper tail test where we state that population 1 has a larger median than population 2, or that the distribution of population 1 is to the right of population 2. So for example here, this would effectively just be saying, going back to the illustration we had before, that if this is D1, then that would be D2. Oh, sorry, other way around. So greater than. And so this test is basically just saying we expect a shift to the right, and then in the lower tail case, we would have the shift to the left. Now, I'm using right skewed shapes in this particular illustration just because of the motivating example. But again, we don't require that both distributions be of a certain shape. They just have to be the same shape. So they can be right skewed, left skewed, symmetric, whatever. They just have to be of the same shape when we're running this type of comparison. When we studied the signed rank test, we went through a description that was meant to illustrate, well, I guess illustrate or demonstrate how the sampling distribution of the test statistic, or how the distribution of the test statistic would behave, or what it would look like. For the Wilcoxon Rank-Sum Test, that logic is almost the same. So since we are dealing with rank sums, and our test statistic is the sum of the rank from the first population, whichever one we declare to be population 1, it follows that the lower bound on this particular population or on the test statistic would again be 0. Okay, so it's possible that if you had two samples and one of the sample had no values for some reason, then the lower bound on the test statistic would be 0, though that would be very rare. And then the upper bound would be the max of all of the total ranks. So in this case, you can see that the formula we're using here is pretty much the same as what we used in the signed rank test case. So recall, for the signed rank tests, right, we had the maximum of W equals n times n plus 1 over 2. This is essentially the same thing. We're basically just saying it's the sum of the total sample size across both samples. plus 1 multiplied by the sum of the total sample size across both samples, right? So this is not different really from 1 n times n plus 1 over 2. It's just that we're considering each sample's contribution separately. So the range for the test statistic is going to be between 0 and the maximum of the sum of the ranks. So if the medians of the distributions are equal to one another, then we can say that the median of the test statistic distribution is going to be n1 divided by n1 plus 2 multiplied by the maximum value. So that gives us a median of n1 times 1 plus n1 plus n2 over 2. So this is going to be at the center of the distribution of our test statistic, right? So we will expect something like this. So we'd have 0 here. We would have 1 plus n1 plus n2 over 2 here. N2. And then in the median here, I'm just going to move this up a little bit. Okay, so at the middle here, we're going to have n1, 1 plus n1 plus n2. And then we might have something that looks like this. So same idea as what we were working with before, but we have a function of 2 sample sizes now. So as a result, we're going to have a different table to utilize because we have to consider each of the sample sizes that are being contributed. More on this in a moment. Okay, so for the same reason that we had established for the signed rank test, if the median is at n1 times 1 plus n1 plus n2 over 2 for the distribution of the test statistic, that means that the 2 critical values are going to be symmetrical about the median as well. So our table, which will give us the upper critical value, which means that if we need a lower critical value, we can use the formula given in equation 2 to find that value. And again, this is the same idea as what we have with the signed rank test, but all we're doing really is taking into consideration that we have an extra sample of information. All right, so the upper critical values for the Wilcoxon Rank-Sum test can be found in the Wilcoxon Rank-Sum table of critical values. So that's given here. So you can see that this table has a sample size for n1, a sample size for n2, and then it has a significance level here. So the structure of this table is like an ANOVA table. So we have, in the ANOVA table, we had df1, df2, alpha. Here we have sample size 1, sample size 2, and alpha. Now, one of the obvious constraints here is that the table only gives us up to a value of 10 for n1 and for n2. And the table forces a minimum sample size of 3. But this is a reasonable restriction, because if you think about a sample of data, if you have less than 3 observations, you don't have enough information to compute variance. So we would require at least 3 observations is reasonable to say that it is a valid sample. Okay, so we have a restriction of having 10 observations in both, or we have a restriction that we have to have between 3 and 10 observations in both samples in order to use this particular table. So like we saw with the signed rank test, and like we saw with the sign test, we can use an approximation to the test statistic that's based off of the normal distribution. Okay, so that approximation is given on slide 10. So here we have n1 greater than or equal to 10 and n2 greater than or equal to 10, then the sampling distribution of W can be approximated using mu equals n1 times 1 plus n1 plus n2 over 2, and sigma is equal to the square root of n1 times n2 multiplied by 1 plus n1 plus n2 over 12. Using these values, we can standardize our test statistic, W, and that will become a standard normal value, which means that on step 3 or on step 4 of our hypothesis test, we can now use the standard normal table rather than the Wilcoxon table. Okay, so that's the setup of the test. We're now going to work through 2 illustrations. The first illustration, we're going to work with the salary data. And as you will see in that illustration, we're going to have to use this approximation. Then we will look at a second illustration where we can work with a data set that has the required sample sizes to use the table so that we can see an example of how the table would work, an example of how the Wilcoxon Rank-Sum table would work. Does anyone have any questions so far? I felt like I'm going pretty quick, but hopefully most of this looks familiar. Okay, so returning to our data set that has the salaries for 10 female professors and 13 randomly selected male professors. At the 5% significance level, do the data provide sufficient evidence to conclude that the median salary for male professors is greater than that of female professors? All right, so we are testing to see if the median salary for the male professors exceeds that of female professors. So let population 1 be the salaries for the male professors. Okay, so therefore W1 is equal to the sum of male ranks. Now, when we rank data in a rank-sum test, we rank it as a whole. So instead of ranking each population separately, we rank from 1 to the total value. Okay, so to rank 1, assign ranks from 1 to n1 plus n2. Okay, so in this case, that means we're going to assign ranks from 1 to 23. So 2, that is treat data as if it is pooled together. Okay, so we're basically ranking as if it's one large collection of values and not 2 separate samples. Now the values are already ordered for us, which helps. So we're basically just going to be bouncing back and forth between these observations. Okay, so I'll write the ranks beside the male and female values using the table that's shown here. Okay, so for example, rank 1 goes to 62,884. Rank 2 goes to 71,065. Rank 3 goes to 78,785. Rank 4 goes to 81,000. Rank 5 goes to 84,000. Rank 6 goes to 84,200. Rank 7 goes to 86,100. Rank 8 goes to 91,000. Rank 9 goes to 91,100. Rank 10 goes to 97,032. Rank 11 goes to 97,247. Rank 12 goes to 103,750. No, that's wrong. That's rank 13. No, it's rank 14. Sorry, rank 12 goes to 107,200. Rank 13 goes to 100. No, I was right. I am losing my mind. Yeah, 103 is small. Come on. There we go. 104. That was probably confusing if you're attention. Does this guy know magnitude or what? Okay, and then rank 18 goes here. 19, 20, 21, 22, 23, 5, 6, 7, 8, 11. Just going to make sure I 13, 14, 15, 19, 20, 22. Yeah. All right, does that make sense? Any questions? So again, when we're using the rank-sum test, we rank as a whole. That's the big thing. So we rank across both samples at the same time as if it's one large pool. All right, so the sum of the ranks here is going to be 152. So that's actually going to be the test statistic for our hypothesis test. Since we declared the males to be population 1, that's going to be W1 for the corresponding test. Okay, so in running the test, we have the first one is SRS for each population. So we'll call this population 1, population 2. Okay, so we were told earlier that these were both simple random samples and that they're independent. We know they're independent because it's a collection of female and male professors in each population. So that would imply independence in the context of how we discuss it. The second assumption, I believe, is the distributional assumption. Oh no, so these two are the same. So then here we would have independence. So we can do this generally across both, right? Because it would be the independence of both samples. And then number 3 would be same shape. So here we can say assume true since salaries are known to be right skewed. Okay. But if we wanted to, this would be easy to check, right? So we can check this using a histogram or box plot, for example, right? So we just need a visualization of the shapes of the data that we're working with, and then we can compare them to see if they're similar. Somewhat, what's the word? Subjective, like how similar do they have to be, but for the purposes of the illustration, we'll assume that this is intact. Okay, so step 1, we have our null and alternative hypothesis. So we're gonna have eta 1 is less than or equal to eta 2 versus HA, eta 1 is greater than eta 2. So again, we declared the males to be population 1. We want to know if there's evidence that the male salary exceeds the female salary. So we have an upper tail test in this case. Right. On step 2, we have our significance level. Actually, I think I'll just fit this all in the same line here. Or no, I'll write this out in full just so that we have the calculation. Okay, and then on step 3, we've already computed this, but this would be our test statistic, W1. So this again is the sum of the ranks from sample 1. So this is going to be, as we showed on the previous slide, 3 plus 5 plus 6 plus 7 plus 8 plus 9 plus 11 plus 13 plus 14 plus 15 plus 19 plus 20 plus 22, which is equal to 152. Okay, so for step 4, we are going to use the normal approximation for the test statistic. Okay. So since n2 is greater than 10, use z is equal to w minus, and then we had n1, 1 plus n1 plus n2 divided by 2, which is divided by the square root of n1, n2, 1 plus n1 plus n2 over 12. Right, so this is going to give us 152 minus 13 times 1 plus 13 plus 10 divided by 2 divided by square root of 13 times 10 times 1 plus 13 plus 10 divided by 12. And this is equal to 0.248. Okay. So now step 4, this can be done in the usual ways, right? So we can take the critical value approach, or we can take a p-value approach. Okay. So it's an upper tail test at the significance level of 0.05. So that means that we have a size of 0.05 in the upper tail. The test statistic that makes, or the critical value that makes this true is 1.645. So we can see that our test statistic here is z is equal to 0.248. So the critical value approach is going to give us no evidence to suggest a difference. And if we take the p-value approach, okay, so we have 0 here. We'll mark down our test statistic to 2 decimal places because of the structure of the normal table. All right, so the p-value is equal to the probability that z exceeds 0.25. Okay, so if we go to our standard normal table, okay, I'll just do it the proper way. And we look up 0.25. So we have 0.2, 0.5, 0.5987. Okay, then that means that here we have 1 minus 0.5987, which is equal to 0.4013. Okay, so regardless of the test that we take, we do not reject H0. And then on step 6, we can say at the 5% significance level, the data do not provide sufficient evidence to suggest that the median salary of male professors exceeds that of female professors. All right, and that's your Wilcoxon Rank-Sum Test. Again, this is our non-parametric alternative to the independent two-sample t-test. Does anyone have any questions? Okay, not seeing any. All right, so let's go through one more example of the Wilcoxon Rank-Sum Test, but in this illustration, we're gonna look at a situation where we can use the table that is provided to us. So we have the following. A college chemistry instructor was concerned that students who had less than 2 years of high school algebra would underperform compared to students with 2 or more years of high school algebra. The table below gives the final chemistry grades for 15 randomly selected students. All right, so in the first column, or the first two columns, or first column of the table, depending on how you want to look at this, we have 6 final exam marks: 58, 61, 81, 64, 74, 43. So these are the final grades for 6 students out of the 15 that had less than 2 years of high school algebra. In the other portion of the table, we have 9 scores. So these are the final chemistry grades for 9 students who had 2 or more years of high school algebra. All right, at the 5% significance level, do the data provide sufficient evidence to conclude that the median of the final grades for students with less than 2 years of high school algebra is less than that of students with 2 or more years of high school algebra? Okay, so we want to know if the grades of the students that had less than 2 years of algebra exceeds that of this, is less than that of the students that had more than 2 years, 2 or more years, sorry, of high school algebra. Okay, so let's assume that our assumptions are intact. In this particular example, you can see that what we're doing here is we're letting population 1 be students with less than 2 years. Okay, right, so we have the lower tail test. If we want, and we want to test that the students that had less than 2 years had a lower median score than the students that had 2 or more years of high school algebra. So it follows that population 1 has been declared to be the students that had less than 2 years. We're testing at the 5% significance level. Now on step 3, you can see what I've done is I've arranged the 6 values of interest from the first population, or from the first sample, provided the ranks, and then we have the 9 values of interest from the second sample, and the ranks are provided there. Now you notice that we've had to break 2 ties along the way. Okay, so this has been done in the normal way. So for example, here, this 8.5, that's going to be rank 8 plus rank 9 divided by 2. And this 11.5 is going to be rank 11 plus rank 12 divided by 2. Okay, so tie breaking is done in the exact same way for the rank-sum test as it was for the signed rank test. Again, we're assigning ranks as if the data is one large pool of 15 observations. So we're ranking from 1 to 15. Since we have declared the students with less than 2 years to be our first population, our test statistic here, W1, is going to be 1 plus 3 plus 4 plus 5 plus 8.5 plus 11.5, which is 33. So this is our test statistic for this particular Wilcoxon Rank-Sum test. Any questions? All right. So let's take a look at step 4 using each approach. So if we take the critical value approach, you can see here that what's happening is we're computing the lower bound, right? So this is the maximum. Well, it's not exactly the maximum, but this part here is n1 times 1 plus n1 plus n2, and then the 63 here is the W alpha. So if we were to sketch this distribution out, we would have something that looks like this. So here we would have 0. At the maximum, we would have n1 plus n2 multiplied by 1 plus n1 plus n2 divided by 2. All right. Okay, so we need to move this over just a little bit. Okay. All right, and at the middle here, so that's going to be our median value, which for us is n1 times, I need to go back and look this one up real quick. Okay, so right here in the middle, we're going to have the n1 times 1 plus n1 plus n2 over 2. All right, now let's say right here, draw this line straight down. So this is going to be W alpha over W alpha. So that's going to be W 0.05. All right, so we go to our Wilcoxon Rank-Sum table. Okay, so our first sample size is going to be 6. So that's the sample of the students, the sample size for the students that had 2 or less than 2 years of high school algebra. Our sample size for the second sample is 9, and our critical value in this case is going to be 0.05. Okay, so that gives us a upper test statistic of 63. Okay, so right here we have the value 63. So you notice that we have that number here and we have that number here. Okay, so that's where the 63 comes from. Now the 33 is the value for the lower table here, lower tail here. So we have W1 minus alpha, which is equal to 33. Okay, we're performing a lower tail test, so we can now take our test statistic, which was also 33, I believe. Yep, and you can see that that sits right on the critical boundary, so W1 equals 33. So that means that we can reject the null, because with the critical value approach, we reject when the p-value is less than or equal to the critical, or when the test statistic is less than or equal to the critical value. And then if we were to look at the p-value approach, right? So what we would have here is another sketch of our distribution. So the points on this are going to be the same. Oh man, I've been trying. Let's count to 8. Okay, whatever. Get the point though. Okay, so this again is going to be the max. Okay, so we would mark down where our test statistic is located. Okay, so we're going to say right about here, for example. So this is W1 equals 33. All right, now what we'd have to do is we would basically take the lower tail test statistic value and we would move it into the upper tail. So we can do that in the same way that we did in the previous illustration. So basically we're going to call this thing here, for example, W1 plus. That's going to be N1, 1 plus N1 plus N2 minus W1. Right, so you can see we're just doing the same calculation from before. So that's 96 minus 33, which is 63. Right. Then we go to our Wilcoxon table. Okay, so we have 6 degrees of freedom and we have 9 degrees of freedom. And what we're doing here is we're moving our way down the line and we're looking for where 63 would fall in. In this particular case, you can see that we are actually equal to 63, which means that the p-value is equal to 0.05. Okay, so since the size here, then the size here is the same. Okay, so therefore, the p-value, which is the probability that W is less than 33, is equal to 0.05. And then since the p-value is equal to alpha, we can still reject. So then we can conclude at the 5% significance level, the data provides sufficient evidence that the students with fewer than 2 years of high school algebra have a lower median semester average, have a lower median final grade compared to, than those with at least 2 years of high school algebra. Okay. Does anyone have any questions? Okay. All right, so if there's no questions, that brings us to the end of our discussion on the Rank-Sum Test. Oh. Same as alpha or W1 is rejected. Yeah, so the rule is the strict rule is p-value less than or equal to alpha means reject H0. So then for the critical value, I mean, it depends on the tail you're in, but in general, we can say if test stat equals critical value, reject H0. It's just most often we don't get p-values being directly equal to the significance level, mainly because of the t-table and how the t-table works. But in the situation where they are equivalent, you can still reject. Okay, so that's the Wilcoxon Rank-Sum Test, which is again our alternative to the independent two-sample t-test. It's a less restrictive test because we only require the populations to have distributions that are the same shape. So we don't require, for example, normality to be assumed for each population. The last non-parametric approach that we are going to study is the Kruskal-Wallis test. So that will be lecture set 10, and that'll be what we look at on Friday. The Kruskal-Wallis test is the alternative to the one-way ANOVA. So after that, we don't have any other non-parametric procedures to look at. So we're only considering alternatives up to the alternative for the one-way ANOVA, which means that on Monday next week, we will start linear regression. And the first week of regression analysis will basically just be a review of simple linear regression. Okay, so with that, I will leave you guys for today. And if anyone has any questions, as always, please let me know. And otherwise, I will talk to you on Friday afternoon.